Welcome everyone to another great workshop event here as part of our Hack Africa series. This is the first part of a two-part introduction to blockchain event, and we are happy to be joined by Laurence Kirk, who is the CEO of XtraP. So Laurence, if you want to go ahead and get started. And as another reminder to everyone, feel free to throw those questions in chat and we will be sure to get those answered here as well. And also go ahead and look in chat. George posted some important links for Hack Africa in there as well. So feel free to check those out as well. Thank you.
Great. Thank you, Daniel. Thank you, George. And hello, everybody. Good to be here to the first part of our introduction to blockchain. Just give a little introduction to who I am and what I represent. I run a company, XtraP. We're a consultancy. We consult around blockchain and cryptography. Based in Oxford, we've been going since about 2015. Really excited about this space. I love doing community education, so it's great to be able to pass on some of our experiences and knowledge to all of you. So I hope you enjoy that. Thank you. Okay, too long to read about blockchain. It's all about providing a trust layer without a central authority. And I'll keep coming back and probably saying this phrase over again, that we don't have a central authority. If you really understand that and bear that in mind, then that will really help you in understanding how blockchains work. Okay, so my view of blockchains, I see them as being made up of a number of components. People might disagree about what blockchains are, but I think there's general agreement about the types of components that are involved. One of the most important ones is the network that forms a blockchain, or a blockchain is built upon. And this is what is called a gossip network. And the reason it's called a gossip network is that information within the network is passed from one node to another. It is gossiped around the network. So nodes just are there to pass on information, to pass on transactions that happen within the network. And the network we have is a peer-to-peer network. It's a network that can be joined by anyone, and there's no central authority, so there's no one controlling this network, so anybody can join it, anyone can leave it, and the network will continue to function even though that people can join or leave at any point. And within that network, as I say, people, the nodes involved, the people involved are there gossiping information, they're passing on the transactions that they have. The second component, perhaps the most important, is this idea of a shared public ledger. And here I am talking about public blockchains. We won't go into other types of blockchains in this introduction, but we're going to talk about the most common, I guess, things like Bitcoin, Ethereum, which are public blockchains. And they have this concept of a shared public ledger. And what this is, if you're familiar with banks, in the old days, they would have a ledger where every transaction that the bank was involved with would be written down. And so you could see everything that was happening in the bank by going through this ledger. And this is the same with a blockchain, with the idea that each node on the blockchain has their own version of a ledger. They keep their own ledger of the transactions that are happening on the blockchain. And it is shared so that every node has their own version. They have their own copy, although copy is slightly misleading because there's no central one that everybody is copying. They each have their own. And it is public because all of the information, all of the data in our blockchain is open to everyone. So everybody can see all of the transactions. Everyone can see everything that is happening. So each node has this shared ledger that they keep, where they keep track of what is happening in the blockchain, and they update the state of the blockchain. So if you think about a blockchain like Bitcoin, this Bitcoin is the number of Bitcoins that a particular account has, the number of Bitcoins that someone has. So each node on the Bitcoin blockchain is keeping track of that, is updating the number of Bitcoins that somebody has. And as new blocks come into the blockchain, into the node, as new transactions come into the node, the node will update their ledger to to take account of the transaction that has just happened. Okay, so that's the second component of a public blockchain, and perhaps the most important. The third one is cryptography, and this is something that we need because we're working across the internet, and on the internet we don't really know who we're dealing with, and we don't know that. Well, we want confidence to know that transactions that have happened, the transactions that we're seeing, haven't been interfered with in any way. They haven't been tampered with, and so we need cryptography involved in our transactions, so that we know that the transaction that somebody sends has not been changed since the person created it. But also we want to have some idea of who that transaction came from. Now, in a blockchain like Bitcoin or Ethereum, there is a pseudo-anonymity going on here. So when I say we want to know who it came from, I don't mean that we will be able to find out who that person is in the real world. We won't find out their proper identity. We won't find out their name. But we will find out they will have an address on this blockchain. They will have an account on the blockchain. And if we see a transaction claiming to come from that account, we can know, because of the cryptography that is used within the blockchain, we can be sure that really did come from them and not from someone else. So this gives us some confidence that there's no impersonation going on here. We can be sure that if we see a transaction that's claiming to come from a particular address, that it really did come from that address. And also, we can be sure that that transaction hasn't been interfered with since it was created and sent. So nobody has changed the amount involved in that transaction. Okay, so those are the three main components, I would claim, that make a blockchain a blockchain. That's what's special about a blockchain, and why a blockchain is different perhaps from a database. But what does that give us? Why do we have these components? And with those components, we have a system that has certain properties. So the system will have transparency, because we have this idea of the data in our blockchain being public. So there is a transparency in our system, because everybody can see what data, can see all of the transactions that are happening. And the state in our system, so things, for example, the number of Bitcoins that somebody has, that is verifiable by people, because you can work out yourself when you see the transactions what the balance of various accounts should be. And the updates to that state are done by consensus amongst the participants in the system. And I'll come on in a moment to how that consensus works. The second property that we have is a resilience. So because of our peer-to-peer network, because of this ad hoc network that people can join and leave at any time, if one node on the network fails, if there's a power failure or some hardware failure, whatever it is, that won't affect the network as a whole. The nodes on the network will still be able to connect to other nodes. They will still be able to pass the information around. They can pass the transactions around. They can gossip this information to all of the participants in the network. So there's a very high resilience of the network. Then censorship resistance is similar, because if you think of this network, it's a global network that anyone can join. If, say, a government decides it doesn't like what this network is doing and try to shut it down, well, they could potentially shut off some of these nodes and try to censor the system in that way. But they couldn't do that to all the nodes. And as long as there are some nodes that still exist on our system that are able to communicate with each other, they can still pass information around. And our system as a whole, our blockchain, can still proceed to work. And then finally, there's the idea of the tamper-proof interactions. Because of the cryptography we have, we know that the interactions on our blockchain have not been interfered with. That gives us confidence about the integrity of the transactions on our network. So that's an overview of the components and what's special about a blockchain. But the technology behind this didn't happen overnight, and it's only come about fairly recently. And if we just have a quick look at the history of that, the internet really started around the 70s, with ARPANET and with various networks being linked together. And then in the 70s, there was a great breakthrough in cryptography, with public and private key cryptography being invented, which is the basis for how the cryptography in a blockchain works and how our accounts on a blockchain are secured. And then towards the end of the 70s, we got the invention of things called Merkle trees, which I won't go into the details of those, but those are cryptographic data structures, and those are the data structures that are used in the blockchains. They're very efficient and secure means of holding data in the blockchain. And then in the 80s, people started to try and use this technology to create interesting things and try to do things like creating digital currencies. But it was quite a difficult process, and people didn't really manage it to create anything robust. And then at the end of the 90s, people were looking at networks in particular, and maybe you're familiar with networks like Napster and BitTorrent. These started to be created. These peer-to-peer networks were created to allow people to share data, and that laid the basis for the networks we use in our blockchain. But still, people were struggling to get together a really efficient and robust blockchain with all this technology. But it came together properly in sort of 2008, 2009 with Bitcoin. And all this technology converged, and we got our first real blockchain. And there's another diagram where you can see different pieces of technology that were involved coming together. And with 2008, 2009, we got Bitcoin, and then it continued. We came to Ethereum in around 2014, 2015. Bitcoin. So this was this proper blockchain, the first really usable blockchain, invented by Satoshi Nakamoto. We don't know who he or she or they are. It's not the person in the photo there. That person had to put out a disclaimer via their lawyers to say they're not Satoshi. An amazing achievement. It's been running since 2009, so over 10 years. Quite amazing for a system to last that long and to last and to work pretty much perfectly for all that time in very adversarial conditions. It was invented, it came about with a paper being released detailing how it would work, and then the software was released in 2009. To give you an idea of its first use, in 2010, somebody bought some pizzas with it for 10,000 Bitcoin. The current price of Bitcoins, I mean, this is an astronomical amount of money that will be paid. You'll be paid for those. So the price of one Bitcoin has risen dramatically since then. The initial, the first block in the Bitcoin blockchain was called the Genesis block. And within that block, there was an area that was set aside for people to put some data in there. And Satoshi, when he created this, put in the headlines of the Times newspaper at that time, which was talking about the bailout of banks because of the credit crisis that was happening at the time. So it's quite an interesting piece of data to put in there to show really how Bitcoin was born and how it came out of the financial crisis of that time. Okay, but if we take a little deeper look into a blockchain and what it's made up of, the data that blockchain has and how it's structured. And this diagram tries to show that. And this is an idealized picture of a blockchain. Each blockchain will do things differently, do things in its own way, implement things how it likes. But this is really, generally speaking, how a blockchain works. So composed of blocks, not surprisingly, the first block called the Genesis block, and then blocks are produced over time, usually a regular amount of time between each block. In Ethereum, they're produced every 12 to 15 seconds. With Bitcoin, they're produced every 10 minutes. It depends how you set up your blockchain, how often these are produced. The blocks are composed of two main areas: an area that contains transactions, and then a header area. And we use cryptography very much in the data structures of these blocks. And what we do when we create a block, we take the transaction area and we take a fingerprint of those transactions, and we put that into the header area. And then we also put other pieces of information in the header area. So we have a timestamp as well. But then we also put a fingerprint of the previous header, the previous block's header in the current block header. So this establishes the link between our blocks. That's where the chain part of the blockchain comes from. And the reason for this is to give our blockchain structure some integrity. Because if you imagine, as we're going along, we're producing these blocks and we're linking them together by these fingerprints. What this means when we do this, linking them together cryptographically, is that if somebody came along after we'd produced maybe a few hundred blocks and came along and brought out another block and said, this is block 2 and here are the transactions in block 2, we could check if that was genuinely was block 2 by looking at the fingerprints that are involved. Because if they wanted to change the transactions that were in block 2, they would have to change the fingerprints that was in the header of that block. But if they did that, they would then have to change the fingerprint that was in the header of block 3, because the fingerprint of block 2 would have been changed, and so on through all of the blocks. So this would be quite a large amount of work that the person would have to do if they wanted to change the data that is in a block. So this is why we have that is what we mean by the chain in a blockchain, and why we link the blocks together in that way. Okay, so that's really, as I say, an idealized data structure of blocks, what they look like and how they link together. Now, how do we come to consensus about the data in the blocks? How do we come to agreement about the state of our system? And there are different schemes for this, different mechanisms to do this. But in Bitcoin and Ethereum, we use a mechanism called proof of work. And the invention of this mechanism was really the great breakthrough that was made by Satoshi that allowed Bitcoin to work, whereas previous attempts at a blockchain had really failed. And I'll just go through now explaining briefly how proof of work runs. So if you imagine a blockchain such as Bitcoin, and what I've got represented here by these dots are the nodes on the blockchain. So each dot is a participant in the blockchain, a node running software that is accepting transactions on our network. This is our network of say Bitcoin, and then the lines are just representing links between these nodes. So each node is linked up to other nodes on the network. So they're all there ready to pass data around the system. And there on the bottom left, we have a blue block representing the latest block in our system. So if you imagine Alice wants to spend some Bitcoin, so she wants to send some Bitcoin, say 1 Bitcoin to Bob, she will send a transaction into the system. So she will create a transaction to say she's spending some of her Bitcoin, and she will pass that transaction to a node on the network. And that node will receive it. And then because it likes to gossip, it will pass that transaction around to other nodes who will carry on passing this transaction around until eventually that transaction is picked up and put in a block. And that block is added and becomes the latest block in our system. And the the information within that latest block and the information in that block and in the previous blocks, and the update that's represented in the latest block, that represents the state of our system. And that is the one source of truth for our system. That is the absolute truth about our system. And once you have that information, it's no use saying you don't like that information or you disagree with it, because that really is the only source of truth we have about our system. So that's so Alice's transaction has now been put in a block and included in the blockchain. The update to the Alice's accounts, the update to Bob's account will have happened essentially by applying that transaction to the state as represented in the block. And that block gets passed around the network. I haven't shown that here, but that block will get passed around the network so that everybody gets the latest state. So that's fairly straightforward, but there's a problem, because we can proceed on and on, adding more blocks. But what happens? How do we come to agreement about the state? Because we could have this situation where in one network, people in the and in another part of our network, people have seen the green transactions. And then in the middle, people have seen neither of these transactions. So how can we represent the state of our network at a certain point of time? Because we want the block, the latest block in our system, to be at the state of network at a particular time. So how can we decide what that should be? Because we have here three potentially different views of what the state of the network is, depending on whether we have seen these transactions. And so what we do is we say, well, each of these nodes in our network, they're all really the same. None of them are special in any way. And so why don't we just pick one of these nodes at random and ask them what their opinion, what their view is of the network at that time, what their view is of the state of our system at a particular time. And we'll ask that node that we've picked at random to produce a block representing that state. And then once they've produced the block, we will all agree to that. We will say, we picked that person at random. This selection was done fairly. If it was done at random, we can be sure there's nothing sinister going on. So we will accept that the person created that block, and that is a fair view of our system. We'll all agree that that block represents the latest view of our system. But as you'll remember from my third slide, we don't have a central authority. So how do we pick somebody at random to create this block? And that is the process that in Bitcoin and Ethereum is called mining. That is the process of selecting someone to produce a block to the latest block within our system. And how this works is that people who want to produce a block, and you do not have to, you can still be involved in the system, you can still be part of this network without being involved in producing a block. But if you want to produce a block, you run some special software, some special mining software that will allow you to do this. And what essentially this software does is to allow you to enter a race to produce a block. And what the race is doing is a race to solve a mathematical puzzle. And what we say is the first person to solve the puzzle will be allowed to produce a block. And so as people are running this mining software, as soon as the previous block has been produced, they will all start the race to produce the next block, the race to solve the puzzle that they need to solve before they can produce the block. And this puzzle is extremely difficult to solve. It's a mathematical puzzle. It is based upon the data that goes into the block. So it is based upon the transactions that have gathered up and the data that they're going to put into the block. And it's extremely difficult to solve. So even though there are, on Bitcoin, there are tens of thousands of people trying to solve this puzzle all the time, and each of those people are doing literally trillions of attempts at solving this puzzle every second, it still takes on average 10 minutes for one person in the world to get the correct answer and to solve this puzzle. And this puzzle has a special characteristic that it has a special, the mathematical function that's involved in this puzzle has a special characteristic that it's very hard to solve this puzzle, but once you have the solution, it is extremely easy to check it. So what the person does who has solved this puzzle is they put the answer to their puzzle in the block that they're creating, along with all of the transactions that they have that represent the state of the system. And then they send this block out to the network and they say, here, I've solved the puzzle, here's my answer. And then everyone that receives that block can check the answer to their puzzle very, very quickly, within a second, within a millisecond. And they will know that is indeed a valid solution to the puzzle. So to find the solution takes 10 minutes, but to check it takes a millisecond, for example. So the person who solved it will pass their block out to the network and everybody can check that it is a valid solution to the puzzle. And once they've done that, they can be happy that this is a valid block and represents the state of the network. Now, regarding the transactions that are in the block, when the other participants in the system, and not just the miners, but anybody in the system, when they receive the block, they can check that the puzzle was solved correctly, and then they can go through the transactions and check that they are all valid. So they can check that these transactions are not spending money, not spending bitcoins that the account doesn't have, so they can check them in that sense. And they can also check the cryptography. So going back to where I was talking about the use of cryptography, and I said it allows us to prove the transactions haven't been tampered with. So when we're checking the transactions, we can also check they haven't been tampered with. So the participants in the system are all adding to the security of the system by checking the transactions and also checking that the person who produced the block was indeed, did have a valid solution to the mathematical puzzle. And the person producing the block is incentivized to produce it by, when they produce the block, they're allowed to give themselves a transaction, give themselves some Bitcoin. So there's what's called the block reward in a block, which they get as a reward for going through this process of trying to solve the puzzle and going through all of this computation to solve the puzzle. Because this computation costs a lot of money, there's a lot of energy used to solve this puzzle. And so it has a real world economic cost. And that economic cost is the basis of the security within our blockchain. Okay. The final problem we could get is what happens if we have this situation where two people create a block at the same time. So here, we've produced the yellow block, and then everybody's mining and running this race to get to the next block, and the red and the green people, miners, both produce a block at the same time and think they're the first to solve the puzzle. What happens then? Well, each one will send out their block to everybody. So everybody will then see there's a potential choice of what the latest block is. So when the next miner comes to mine the block, they have to make a choice which block they should follow, which block is the latest one in the chain. And there's a rule of thumb to do this. And this is down to how this puzzle is run, but there's a way that they can always discover which one of these blocks to choose. And in this example, the beige block has decided that the red block is the one that we should take. And so the chain then continues going through the red block to the beige block and so on. And our blockchain system will continue accepting the red block in that position. And the green block will be dropped. It will become an orphan block. The transactions that were in that block will not get lost because perhaps they will have been picked up and put in the red block, or perhaps they will be taken up and put in later blocks. But the transactions in the system are not lost until they have been confirmed in a block. So there's no data loss there. The only loss they have is that the miner producing the green block will have lost their block reward. So they won't be happy, but the person producing the red block will be happy because they get their reward. So that very quickly is how the consensus mechanism in Bitcoin and Ethereum works. And I say this just to show you really the breakthrough that happened and how we can come to an agreement without a central authority, which was quite a major achievement. Okay, there's a question about that, asking about a monopoly or centralization of mining power. So yes, yes, this is a race, and it really depends upon the person winning the race will be the person with if the more mining power that you have, the more computational power that you have, the better your chances at winning the race. Obviously, there is some luck involved because the way you're solving this puzzle involves taking a guess. But yes, you're right that the more mining, the more power you have, the better. And because of this, the protocol has another aspect as well, and the difficulty in solving this puzzle increases over time because it was assumed that the hardware that people would use would get better over time. So over time, the difficulty of solving this puzzle increases. It takes more computation. So over time, better hardware is needed. But yes, it is true that if you have if you can control most of the mining power, then you would control effectively you could control the network to some extent. And there is the idea of this, and the idea of what's called a 51% attack. If you had 51% of the hashing power in the network, this could give you some aspect of control over the network. But there is still, since everybody can get involved in this network, there is still competition between people. And there is some centralization to some extent. We see this geographically. Certainly there was a lot of people in China, for example, who had access to cheaper energy, so there are large farms, mining farms set up there, although that has changed more recently. And there is some aspects of centralization of hardware as well. So there are only a few people creating hardware for this situation. But yes, there is some centralization of the hashing power involved. But there also is a community reaction against that. For example, in 2013, when it was seen that people had got together and had more than 50% of the hashing power in what was called a mining pool, then people voluntarily left that pool and joined other ones to try to ensure that no one organization had too much mining power. The system is not necessarily getting slower and slower over time. It tries to maintain this 10-minute block time. So as hardware gets better and we can solve this puzzle more quickly, also in step with that, the difficulty of solving the puzzle increases. And so there is a dynamic equilibrium kept within the system that keeps this 10-minute block time. But what I'm talking about now is the proof of work consensus mechanism that is used by Bitcoin and Ethereum. There are other ones, other mechanisms used, say in Polkadot, Avalanche. There in EOS, different blockchains use their own consensus mechanism, and some blockchains have moved away from proof of work because of the high energy cost that it has. Ethereum will be moving away to a different consensus mechanism, to one called proof of stake over time. I'll talk now about Ethereum because Bitcoin was really leading the way. It started in 2009 and was when it came out, there were a number of competitors or copies of it producing similar things, but people were doing very much the same idea of using tokens and passing value between participants. But that was really what the blockchain was limited to, and people would have difficulty making it do much more than that. But then in 2014, Ethereum was invented, and this tried to introduce computation on the blockchain, and this was really the next large step forward. The idea behind this is that people could create small applications called smart contracts. And the network, the underlying network, is very similar to Bitcoin. It uses a similar consensus mechanism and similar idea. But what is actually using on top of that is this idea of smart contracts, so small applications that can run within our system. And similarly, Alice in Ethereum, she can create one of these smart contracts, and she will then submit that to the blockchain, and it will get gossiped around the blockchain participants, so that eventually everyone has a copy of her smart contract. Every node on the system will have a copy of her contract. And then people who want to use that contract can interact with any one of these nodes and can call functions within that contract. And those functions, the computation that happens on Ethereum happens on all of these nodes at the same time. And each of these nodes is running a virtual machine. So on top of the underlying blockchain layer, on top of that, there is a virtual machine that is running, and that is where these smart contracts run. And it's a virtual machine. It's like a simulation of a computer. It's not necessarily very efficient, but it allows us to run small programs, these smart contracts. And when someone interacts and calls a function on one of these contracts, that interaction is done via a transaction that is passed around the network that everybody receives. So everybody will run the same computation within this virtual machine at the same time. So don't confuse this computation with the computation that is being done in proof of work. It's nothing to do with solving that puzzle. This is the computation that is being done as part of a smart contract. And as I say, every node on the network runs the same computation at the same time. So you could see it as being quite inefficient, and in a sense it is, but this is not about efficiency in that sense. This is about being able to verify the computation that is done, and being able to verify the end result of the computation, and being confident about the computation. So this is done in what's called the Ethereum virtual machine. It has some restrictions. So the amount of computation that can be done is limited, and it is represented by this concept called gas. And if you use Ethereum, you will know about gas and the gas price. And every step of computation that is being done on Ethereum spends some gas. And when you send in a transaction, when you try to do some computation in Ethereum, you try to run a function in a smart contract, you have to supply a certain amount of gas up front. That is the amount of that represents the amount of computation that your transaction will do. And each step that your transaction goes through on the Ethereum virtual machine will take away a little bit of gas from that you provided up front. And if that, as it's taken this away, if that ever gets down to zero, then the virtual machine will stop your transaction and revert the state back to what it was when your transaction started. And this gas has a real world cost. It is, you pay for it in Ether, the cryptocurrency of Ethereum. And so that's why you have to now know about the gas price when you're doing a transaction on Ethereum. And the cost of the transactions on Ethereum can vary considerably. It can be extremely high. It can be many tens or even hundreds of dollars, depending upon this gas price. But it is done to prevent denial of service attacks on Ethereum. The second restriction there is determinism, because everyone on the Ethereum network is doing the same computation at the same time when they run the functions in the smart contract. And so we want the state of our system upon each node to be identical after we've done all of these computations. And so all of our smart contracts have to, when they've done a computation, have to produce the same result. So they have to be completely deterministic, and which means you cannot have random numbers in a smart contract, because that could mean that some nodes would produce different results to other nodes. And also that means the third point here is that they cannot get information from say the internet. And so we have to have a different means of getting information from the outside world. And for that, we rely on things called oracles. If we need information from the outside world, we have to ask an oracle for that information. I won't go into the details of oracles, but they get information for you from the outside world and pass it into the network as a transaction. And that means that everybody in the system will get the same information. And it will mean that our computation on Ethereum is deterministic. The languages we can use in smart contracts, we have a choice. The most popular is Solidity. In the next workshop, we'll look at an example of that, but there are other languages available. Solidity is the most popular. If you're creating an application on Ethereum, you have some things to think about because the system is decentralized. For example, if we're playing rock, paper, scissors, you have to remember that this is being done on a public blockchain. So if we have a game that we're playing, the transactions in this game are transparent, so they will be seen by everyone. So if you play a game, the turns in this game and what people are playing on each turn will be seen by everybody. So cheating will be possible because in this case, Bob would know what Alice had played, so he would know how to respond to that. So if we're designing an application for a blockchain, if we're designing for decentralization, we have to be a little cleverer than we do when we're designing traditional applications and find ways of overcoming this fact that we are doing things in a decentralized manner and the fact that our transactions are public. Okay. There are some common practices and patterns and best practices. I'll just give links to these here. I won't go into them in detail. If you're writing smart contracts, and we shall see this in the next workshop, there's a great library that you can use, a great project called Open Zeppelin, and they produce libraries which have a lot of the common functions that you want to write in smart contracts already written for you. And because these libraries are open source and they've been seen by people in the community, you can be sure that they don't have any vulnerabilities and they are safe to use. And they allow you to do things like provide access control to your contracts, so restrict who can call functions on your contract. They allow you to write some of the common applications on Ethereum. So a lot of contracts on Ethereum are designed around providing tokens, and there are different standards to these called ERC20, ERC71, etc. And Open Zeppelin have libraries. They already have boilerplate contracts that will allow you, that give you the code for these. So you don't have to reinvent the wheel and write these for yourself. And then that's the smart contract side. You can write these in Solidity. But then if you want to interact with those contracts and create a decentralized application, there's a whole layer of technology that you need to do that. And this is where this uses libraries such as Web3.js. So this is a JavaScript library that allows, for example, a web page to interact with smart contracts on the Ethereum blockchain. I don't have time to talk about these in these introductory workshops, but just to be aware that that's the technology that you need to go to talk to your smart contracts. And there are some great developer tools for creating smart contracts and for interacting with them. We'll look at one in the next session called Remix. Once you've got familiar with Remix, Truffle is another set of tools that you can use for development. It's a great set written by Consensus. I can highly recommend it. I'll just talk briefly about DeFi, because a lot of the applications on Ethereum blockchain are around that. There are exchanges on blockchain which have a distinction between centralized and decentralized exchanges. This list here is some of the decentralized ones. They are generally not as large as the centralized ones, but they are increasing in use. Generally, they have disadvantages and advantages compared to centralized exchanges. For example, if you use a decentralized exchange, you have control over your funds, whereas on a centralized exchange, you are reliant on the exchange itself for doing transactions for you. But on the other side, decentralized exchanges tend to have lower liquidity, whereas centralized exchanges tend to have more liquidity. I won't go through much more about that. I'll just mention Uniswap, very popular project on decentralized finance. It uses something called constant functions to provide a market for the people who are using Uniswap, so it allows people to swap tokens for each other. So for example, you could swap Ether for a stable coin such as DAI. It incentivizes people to provide liquidity within the exchange by giving them tokens called LP tokens. So if you provide Ether and another token, so in this case, Tether, USDT, they will give you LP tokens as a reward for doing that. And then when you come back, when you remove your liquidity from the pool and cash in these LP tokens, you should find that they have increased in value. You should make a profit by providing this liquidity. And this profit comes from the decentralized exchange having charged fees on other people who have used the exchange. I'm sorry that I'm having to rush through things. We don't have a lot of time and we have quite a lot of questions, so I want to get to a lot of those. I just mentioned also yield farming. This is a concept whereby because people get rewarded for interacting with projects in the DeFi space, and for example, they may get governance tokens for that. Yield farming came about last year as a means of finding out the best place for you to put your tokens, or the best place for you to invest in different projects, and it was done a way to do that automatically. And yeah, won't go through that. Just to mention quickly, flash loans and Aave, these were an innovation that came out around 18 months ago, and it was something that is very specific to the way that transactions happen in Ethereum. And this is a great example of how blockchains have been innovative. So even though decentralized finance has tried to do things that traditional finance has done and do those on a blockchain and do those in a decentralized way, it also has come up with things that centralized finance couldn't do, traditional finance couldn't do. And one of these is the ideas of flash loans. And the idea behind a flash loan is that at the beginning of a transaction, you can get a loan, say of Ether, that gives you capital to do something that you can do something with. So at the beginning of a transaction in a smart contract, you can get a loan from, say, Aave, that you can use this Ether or whatever it is to do with as you like, maybe to try and exploit some arbitrage opportunity that you have. And then you can do various other things in this transaction. But at the end of the transaction, you have to pay back this loan. And because transactions on Ethereum are atomic, all parts of the transaction either succeed and are applied to the blockchain as one item, or they all fail. So either everything happens within this transaction or nothing happens. So effectively, with this flash loan, you get the state at the end of the loan that either you took out the loan at the beginning and did whatever you did with it and then paid it back, or if you don't decide to pay it back, or if you decide that you don't like the results of what you did with this loan and you revert the transaction before it is completed, then the whole transaction is reverted. It's as if that transaction never happened. So it's as if you never took out the loan in the first place. And this is something quite remarkable in the blockchain world, something that you couldn't really see in traditional finance. And effectively, these these flash loans are almost risk-free, and they can be done for very low fees. So a remarkable invention on the blockchain. As they came out about just over about 18 months ago. Yeah, and so just to wrap up, so I want to get to the questions. If you're interested in this area, we have a lot of community resources on our foundation website. We have a lot of information about writing smart contracts, introductions to decentralized finance, introductions to programming on the blockchain, and security on the blockchain. We have newsletters, all sorts on there. So please do go have a look at our website. I'll now go through the Q&A. There's a link to the slides here as well, so you're welcome to have a look at those. Okay, let me have a look at some of the questions, and I can go through those before we finish. So I'm sorry that this has been so rushed, but I do want to get through a lot of the questions. Okay, so I answered the one about the centralization and that, and yeah, so you're asking about user a government tracking a user's transactions. Yes, they could do that, and that is the way that we do see governments trying to regulate blockchain usage, in the sense that the regulation, the control over blockchain happens at the interface between the blockchain and the, if you want to call it the real world, the traditional system. So they can try to control blockchain usage by controlling, say, how bank accounts are, or how banks can interact with blockchains, or how centralized exchanges interact with blockchains. They will maybe insist that you have to do KYC, know your customer, and anti-money laundering activity, and they will prevent or try to prevent people swapping or buying cryptocurrencies for fiat currencies, and try to control blockchains in that way. So that, yeah, exactly, that's exactly where governments do try to control blockchains. But that's only possible if you are going that route in with interactions with blockchains. If you want to start up, and anybody can start a node on Bitcoin or on Ethereum and connect to the network, the government can't stop you doing that, and they will find it hard to track down who you are on the blockchain. How there are some means to try to get at your real world identity from your blockchain identity, from your blockchain address. But if, say, you use a different address each time you do a transaction, then it will be quite difficult for the government to do that. So if you avoid interactions with sort of traditional financial systems altogether, then it is quite difficult for the government to kind of control how your interactions are used. Is there a possibility for true privacy in blockchain environments? Yes, so I've spoken about public blockchains such as Bitcoin and Ethereum, where there's transparency, and that transparency is an advantage because that means that everybody can verify transactions. If you want privacy over transactions, there are some blockchains that allow you to do that and use technology such as zero-knowledge proofs. So, for example, Zcash, Monero, they will allow you to do transactions that hide some details of the transactions that are being done. And there are other blockchains that go into this and that go into privacy in different ways. Zero-knowledge proofs as technology is a way to do that. I've answered the question about disengage slower. We'll be looking at proof of stake. I can mention it next week very briefly. Yeah, I'll do that next time, perhaps. Yeah,
it's on Thursday. Sorry, I've just popped a link to the part 2 of this in there as well. So be sure to go and sign up for that, everyone.
Yeah, I'll talk about proof of stake then. Thank you. How do we upgrade the system? So yeah, that's problematic. So when Bitcoin, for example, wants to upgrade the system, what they have to do is push out new software to people who are running the nodes on the system and ask them to update their software. Now, depending on the type of change that is happening, we could get a situation where the old and the new software are coexisting. So some nodes are running old software, some nodes are running new software, and if the change allows our system to proceed in that situation, that's fine, and that's really called a soft fork. That you can also get the situation where the network, the change is so dramatic that the two kind of sets of software won't coexist, and that is called a hard fork. And typically, that's where people, the people in the system, fundamentally disagree about how the system should change, and so they split the network into two, and each kind of part of the network goes its own way. Thank you for the link about Polkadot. Yeah, the denial service. Okay, that's been explained. Good. Scalability. That's a big problem for blockchains. They do not scale well, generally speaking. You tend to have a trade-off between scalability and security, or decentralization. So you get two of three usually. You can either have good decentralization and good security, but bad scalability, or maybe you cut down on the decentralization and you have better scalability. And for example, EOS has that, is an example of that. But scalability is a huge topic, which yeah, we don't have time to go into, I'm afraid. Yeah. Okay. More questions about that. Next workshop, the prerequisites. There are none. I shall demonstrate some coding, writing a smart contract in Solidity, and I shall use Remix, which is an in-browser development environment. So you can just go to the Remix website, and if you want to follow along with the coding that I'm doing, you can just use that. So that's the only requisite that there is that you have a browser and you can go to the website. Thank you. So teaching JavaScript, learning to learn Solidity afterwards. Yeah, I would say the easiest route to developing on blockchain at the moment is Solidity, and yeah, JavaScript I think is still the most common interactions with smart contracts. The way that different blockchains have developed over the years, a lot of the competitors to Ethereum have seen that developers are really, the developer community knows Solidity best, and so they've followed that really. So a lot of other blockchains are also EVM compatible. Sorry. So for example, if you got something like Thundercore, you can write smart contracts in Solidity on Thundercore. You can write them for Hyperledger. Yeah, you can. A lot of them rely on the fact that people know Solidity, and so they provide that compatibility. Yeah. Consensus on Hyperledger Fabric. Yeah, so there's different consensus mechanisms. They rely on a thing, PBFT, based on Byzantine fault tolerance, which is more of a kind of a vote. The nodes go into a kind of some rounds of voting. They propose a change to the system, and then they have a round where there's voting going on, where the nodes vote about change to the system, and there needs to be a majority of the nodes agreeing to the change. And if that majority, if there is a majority, then the update will happen. But on Hyperledger, that's a private blockchain where there is kind of more knowledge about the network and more control over the network. So something like that is easier. Yeah. Okay, I think, have I covered all the questions? I'm sorry, I've rushed through them so much. I was trying to get in on time. If there are any more questions, I'm happy to carry on, but I don't want to take up more time.
I believe there was one that was just asked
Okay.
a couple seconds ago. And we can conclude with that one.
Yeah. How does Solidity compare? So yeah, there are a number of alternative languages for writing smart contracts. Solidity is, I think, the most popular, and so if you're starting out, it's probably the best bet. It's certainly, it has its drawbacks, although it has improved a great deal over the years. The approach it took was, it was designed as a blockchain language from, it was created as a blockchain language, so it was designed for that from the start, which I think is perhaps a better way to do things, rather than starting the other way around and taking an existing language and trying to adapt that to a blockchain. Because the problem with that approach, with trying to restrict something like, say, Java, is that you have to then try and sort of cut out parts of maybe some of the libraries and parts of the language so that it will work safely on a blockchain. And I think there's more chance of that going wrong, rather than having all of the kind of the blockchain features built in from the start and being part of the mindset initially. But certainly it's had its problems. It's had its security problems. There's lots of issues that you should be aware of when you're working with Solidity. But it has improved a great deal. But if you're going into it from traditional languages, you will be quite annoyed, because a lot of features that you're used to aren't there from natively. So things like string manipulation is not provided natively, which is very annoying. The fact that people want to write log statements to print so they can debug their contracts is not there natively. But there are ways around that. But it can be a bit of a shock for people initially. But the syntax itself is similar to perhaps the JavaScript. It's quite easy to read, but you have to get your mindset into the smart contract mindset, the way that the blockchains work. Okay, but yeah, certainly it's well worth checking out other ones as well. Yeah, so you've got a link to reach there. Okay.
Awesome. Well, I believe that wraps up the last of the questions. So yeah, thank you so much, Laurence, for the great presentation and answering all of those questions. Very educating. And so also thank you to the audience for engaging in the chat session and asking all these great questions as well. Just as another reminder, the second part of this two-part Introduction to Blockchain series will be on Thursday at the same time as well. And also this event was recorded and it will be on our YouTube channel by tomorrow. So if you want to go back and look through the slides and watch the video, just stay tuned in the Discord channel. We'll get that posted here shortly. But yeah, I believe that wraps it up. Have a great rest of your day, morning, evening, wherever you may be located. Thank you.
Thanks a lot, Laurence. Fantastic event.
Thank you.
Bye, everyone.
Bye.